Hello and welcome. My name is Jerry Folgert. This video, brought to you by KnowGIS.com, that's spelled K-N-O-W-G-I-S, provides a simple, broad-stroke overview of geographic information systems. Here's what I have planned. First, we'll look at the history of GIS and some existing definitions of GIS. Next, we will explore and define spatial data and get a glimpse of basic spatial data principles, which will then lead us to a discussion on spatial referencing systems, and then onto spatial data models. Onward, we'll have a simple discussion on portals and government websites where we can obtain or download data for our project. We'll describe a few other software packages other than ArcGIS which facilitate GIS activities, and we'll explore simple spatial analysis. I know some of you are probably thinking, well, what about cartographic design and map making? That's a pretty important part of GIS. Yeah, you are right. Our KnowGIS training series covers cartography and map making. Check out our website for more information. GIS is more than just a software package. By learning and understanding the basics of geographic information systems, we'll have a foundation to stand on if and when we decide to learn a particular GIS software package. Planet Earth, our planet, is an amazing place and is headquarters for Humans Incorporated. Humans, such as myself, share the planet with a variety of other life forms, including reptiles, plants, insects, and the amazing bonobo. Did you know that the bonobo is considered a pygmy chimpanzee and is endangered? It's found only in the wild in the Republic of Congo. And believe it or not, the bonobo shares a phenomenally similar DNA structure to human beings. Some scientists claim it is the closest relative to humans on planet Earth. Researchers from around the world, including Japan, are studying the bonobo and using GIS to map the spatial distribution of existing populations. The population of the bonobo is unknown, but it's estimated to be about 100,000. The population of Homo sapiens on planet Earth is beyond 7 billion, which is about the same number of bacteria in our mouth. Many people on this planet seem to have an unquenchable thirst to gain more knowledge and understanding of our planet. The complex natural systems found on planet Earth continue to amaze humans, and many humans with inquisitive instincts have a desire to learn about these complex systems. So much of what we do day to day has a spatial component, and so do the complex systems on our planet. GIS is one of the powerful tools in our arsenal to help us understand our complex world. In addition to the natural world, we as humans have created infrastructure such as roads, bridges, and power lines, which are theoretically supposed to help make our lives better or easier. In a nutshell, if we were to Wait a minute, what does that mean in a nutshell? Does it mean if we were to take all the information about the world, write it on a piece of paper, and then crumple that piece of paper, it would fit in a nutshell? Probably not. Anyway, so planet Earth is made up of many complex features, and geographic information systems can help us keep track of these complex features in a simplified manner. For example, a wildlife biologist studying American bison and grizzly bears may have an interest in learning about the range of the animal, where it travels, what it eats, and what is its desired habitat. Using automated data collection systems, the movement and home range of animals can be determined, at least for a period of time. Time is an essential part of any measurement system, including GIS. The term temporal specifically refers to times and dates. The positions of these critters can be viewed in conjunction with other geographic information assets, such as a satellite image or a slope map. Emergency response crews, those individuals who respond to emergency calls, for example, 911 calls in the U.S., may have a desire to know, first of all, where the emergency is located, how long it may take emergency response vehicles to get to that location, and the distance to the nearest hospital. Using GIS, we can build a database to reflect existing infrastructure, including roads and buildings, and we can use GIS to visualize this data, along with address information, utilizing dynamic segmentation or routing we can determine the impedance or resistance between the location of emergency response crews and the emergency. What are examples of impedance or resistance? For example, a gravel road may offer more resistance in traveling as compared to a paved road, or a washed-out bridge would offer resistance in getting to the emergency. Resistance equates to a longer travel time. A farmer or rancher in Canada may wish to track livestock on his or her property. As it relates to agriculture, if the farmer is growing canola, a certain variety of rapeseed, and grasses to be dried and used as food sources during the winter, there may be a desire to inventory existing features on the property, keep track of crop size in acres or hectares, and make better growing decisions by understanding underlying soil conditions, sources for water or irrigation, and weed control. In years past, people involved in the previously mentioned tasks had to rely on massive amounts of paper material, hand-drawn maps, and their own imagination to consider alternatives, to view their inventory, and to make decisions. A geographic information system is a tool that has the potential to help us manage, analyze, and display geographic information or spatial information on a computer. In simple terms, a geographic information system combines computer cartography or map making with a database management system. In very simple terms, the GIS stores a graphical representation of real-world features and information about the real-world features, also known as attributes, that are linked to the graphical representation of the real world. These features are referenced geographically, or sometimes referred to as geocoded, to some type of coordinate system. Attributes are elements of data that are connected or related to the spatial data. The attributes, in simple terms, describe the spatial features. Let's take a look at a simple example. A fire hydrant could be represented in the GIS as a point. This is the spatial feature. Information describing the hydrant, such as valve size and the installation date, would be considered attributes. GIS data made up of the spatial component and the attributes can be referred to as geographic information assets. Within the GIS database, a user can enter, manipulate, analyze, review, correct, and visualize data that are associated with spatial elements on the fabric of our planet. Each geographic information asset reveals some different aspect of a place on our planet, planet Earth, or on another planet. Yeah, and by the way, GIS can be used as a tool to explore other planets. Scientists have used mathematical expressions to represent the shape of Mars, for example. A reference ellipsoid is a mathematical representation of the physical planet and its surface. Temperatures on Mars at the datum or reference surface level, there is no sea level that we know of, vary from minus 135 degrees to plus 28 degrees Celsius. An unprotected bonobo or human on the surface of Mars would probably freeze in a matter of minutes. They may also die of exposure to the near vacuum. There are also high levels of radiation from the sun and elsewhere. Other than Earth, Mars is the most hospitable planet in our solar system, at least to humans. A few years ago, I rode my bicycle up to Mars with a bonobo friend of mine, and I captured this video. The atmosphere of 5.6 millibars of pressure is 1/2 of 1% of Earth. Yeah, it was pretty tough to breathe up there. If you ever get up there, it's pretty crazy. I certainly appreciate our planet. Now, back on planet Earth, the activity of measuring and viewing natural and human-made phenomena have been going on for quite some time. Humans have drawn on sand, rocks, paper products, plastic, and this plastic is sometimes referred to as mylar. Recording information about our planet by drawing maps manually was a precursor to the modern-day mapping and geographic information systems. A glass-top table, referred to as a light table, was used for visualizing and viewing mylar overlays. Mylar overlay sheets contain ticks or registration marks which facilitate or help with the alignment of each sheet. Each mylar sheet would store or represent a thematic layer or a theme found on planet Earth. Some examples of thematic layers or themes include water features, such as rivers and lakes, or transportation features, such as highways, roads, and railroads. When the mylar sheets were overlaid on top of one another, spatial patterns could be viewed. Researchers and mappers could then place a predefined grid over the top of existing thematic layers. Because each grid had a known size and location, information stored within each cell could then be entered onto a punch card. The punch card was then piped through a mainframe computer for simple analysis. A punch card, huh? Well, I wonder if we could start a new company designing and manufacturing greeting cards specifically for boxers, made of punch cards. That's the punchline. A punch card, also known as a holograph card or an IBM card, is a piece of stiff paper that contains digital information representing the presence or absence of holes in predefined locations. Punch cards were widely used throughout the 19th century for controlling textile looms, and eventually found their way in the 20th century for data input, processing, and data storage for computers. Simple maps were then generated using the dot matrix printer and the vector pen-based plotters, often referred to as a pen plotter. A pen plotter would produce a map in a way very similar to a young kid using a crayon on a large piece of paper. Apparently, the first computerized GIS evolved in 1964, thanks to our friends in Canada. The Canada Geographic Information System was designed to analyze an inventory of land as part of a rehabilitation and development agency program. During the 1960s and 1970s, university research students and government employees continued research on geographic information systems, developing new software, techniques, and procedures for capturing, storing, and visualizing spatial data. Researchers at the Harvard Lab for Computer Graphics produced a program called Odyssey, which was the first modern vector-based GIS. We'll talk more about vector in a little while. Jack Dangerman, who studied at the Harvard Lab for Computer Graphics, co-founded Environmental Systems Research Institute, also known as ESRI. Let's step forward out of the history of GIS and look more at what GIS is. Some consider GIS as a science. Others think of GIS as a tool. There are many folks involved in this debate of defining what GIS is. This debate continues. Geographic information systems, also known as geographical information systems, do not, unfortunately, have an absolute agreed-upon definition. Different definitions of GIS have evolved in different areas and different disciplines. A GIS at least consists of a database, map information, and a computer-based link between them. A broadly accepted definition of GIS is one provided by the National Center of Geographic Information and Analysis. A GIS is a system of hardware, software, and procedures to facilitate the management, manipulation, analysis, modeling, representation, and display of georeferenced data to solve complex problems regarding planning and management of resources. A geographic information system has evolved and become very useful for many disciplines. A GIS allows us to enter new data, store the data, retrieve it, analyze it, model it, and it facilitates the creation of a cartographic product or a map. Before we go much further, I'd like you to keep in mind the definition of initialism. Initialism is a term formed from the initial letters of the several words in its name. Initialism is different from an acronym in that an acronym can be pronounced. GIS is an initialism formed by using the capital components from the words Geographic Information Systems. Unfortunately, there are people that use or say the phrase GIS system, which really doesn't make sense. If you have bad diarrhea or a bad bowel movement, would you say you're having a bad BM movement? If you were thirsty and had a craving for orange juice, also known as OJ, would you ask your waitress or waiter for some OJ juice? Try to keep that in mind when conversing about GIS. A geographic information system is just that. It is a system for storing and manipulating geographical information on a computer. This system is often comprised of computer software and spatial data. And yes, humans are a big part of this system. Let's consider representing, storing, and displaying a real-world feature in a GIS. Let's use water wells as an example. The goal is to take these real-world complex features which have significant detail and represent these features in a computer through a process called simplification and generalization. In other words, we are identifying a real-world feature and then mapping it, which equates to determining its position, and then we're assigning attributes to that mapped feature which describe the well. It is up to the creator of the database to determine the level of detail stored in the feature attribute table. An attribute table associated with the well features may include just an identification number, or they may include information on the date the well was drilled, the pH of the water, and the depth of the well. If the date the well was drilled was recorded in the database, we could visualize how data changes over time. We will see this in action in a later tutorial. In this example, our well data is represented as vector data. The background image is considered a raster dataset. We'll discuss vector and raster data models a little bit later on. Hydrogeologists have generated another geographic information asset representing the spatial distribution of potentially toxic substance that has entered the aquifer. This thematic layer is a modeled layer, meaning it doesn't necessarily reveal exactly what is going on in the aquifer. In this case, numerical models designed by human beings were used to predict or determine the approximate spatial distribution of the substance. Using GIS software, we can visualize a composite map revealing these geographic information assets. In this simple example, we can visually inspect the data and determine which wells are within or near this potentially toxic plume. I just had a glass of water. I think my well is contaminated. Instead of only a few wells, imagine we had many water wells. Imagine the plume or the modeled spatial distribution of the toxic substance was a little more complicated. Now we can instruct the software to automatically select all of the well features that are within the plume. Automated GIS procedures allow us, as humans, to do in the computer environment what we could do in our minds. It may appear arbitrary that the positions of the wells just happen to align properly with the satellite image. One of the magic aspects of geographic information systems is that GIS allows us to view many different geographic information assets together as overlays in the same spatial domain. The spatial alignment of data in a GIS is not automatic or spontaneous. Even though there's a lot of numerical computations going on in the background, and it may seem like we don't need to really care about what's going on, we really should. We should at least have an understanding of spatial coordinate systems. But there are legitimately thousands of different coordinate systems that exist. Each coordinate system is defined with some mathematical formula. How can any GIS keep track of all this stuff? How can any human or even bonobo keep track of all this stuff? The concept and notion of a spatial referencing system is one of the most fundamental and interesting aspects of GIS. And we as GIS users need to understand it. The subject of spatial referencing systems can also be daunting. Let's try to tie together the concepts of a spatial referencing system. If we wish to store real-world information in a geographic information system, such as our individual or multiple water wells, the property of location is important. The location of real-world objects is partly defined by a coordinate system. Various coordinate reference systems exist. There isn't just one. In each coordinate system, the geographic location of a feature is described mathematically using coordinate values. Even though these values may differ in a numerical sense, they still represent the same geographic location or position. In this example, we see the location of a tree, one single tree, stored in 3 separate spatial referencing systems. Why is it important for us to have an understanding of coordinate reference systems? What's the big deal? A common problem or situation in using GIS data arises when different data sets are stored in different coordinate reference systems. Here's an example. If we were to add 2 geographic information assets to ArcMap and they show up in 2 different locations on our screen, more than likely the reason is the data are stored in different coordinate systems and the software was unable to determine the coordinate reference system of one or all of the geographic information assets. Every GIS dataset is in some coordinate system, right? Either a geographic coordinate system using longitude and latitude expressed in decimal degrees, or a projected coordinate system, which is a flat 2-dimensional representation of the Earth based on a sphere or spheroid, and a geographic coordinate system using linear measurements for coordinate values. Data stored in a computer-aided design or a CAD system may be stored in an arbitrary coordinate reference system designed by an engineering company. All right, here is an interesting thought. Sometimes the coordinate reference system of a data set isn't defined, even though the data set is, in fact, in a coordinate reference system. What does that mean? Before we answer that, let's define what a coordinate system is. A simple definition is a system that uses coordinates to establish position. Another definition is a method of representing features in a space of given dimensions by coordinates from an origin. A coordinate reference system is related to the real world through a datum. The datum provides a relationship of a coordinate system to the Earth. We must consider the datum when working with geographic information assets. All right, we're opening up a whole new can of worms here. Datums, spheroids, and ellipsoids. Unlike local surveys, which treat the Earth as a plane or a flat surface, all coordinate reference systems, especially over a broad area, must take into account the actual shape of the Earth. As we know, the Earth is not a perfect sphere. Some scientists refer to the irregular shape of the Earth as a biaxial ellipsoid. The Earth is nearly spherical, but it has equatorial bulging, making the radius at the equator about 0.3% larger compared to the radius measured through the North and South Pole. In simple terms, think of the Earth as not being quite a perfect sphere. In fact, it's actually irregular in shape, which makes measuring coordinates and altitude far more difficult. The Earth, an irregular-shaped sphere, is often called a geoid. This irregular shape makes it difficult to calculate precise measurements at various points on the Earth's surface. The Earth's shape, or geoid, and reference points used for map preparation are called the datum. A common horizontal datum in the U.S. is the North American datum of 1983. In a perfect world, mapmakers, cartographers, and GIS practitioners choose a datum that best fits their need for the area they are mapping. After selecting an appropriate ellipsoid, the next step is to select the most appropriate mapping of the spherical coordinate system onto the selected ellipsoid. It's important to remember that the Earth is dynamic and changing all the time. During diurnal movements caused by ocean tides and the moon, the shape change of the Earth can be as much as a meter. All the maps that we create eventually will have distortion and errors in them as compared to the real world. As a reminder, data stored in a GIS is only a representation of the real world and is in an estimated positional realm. Today, there exists hundreds of different datums, though some of the most commonly used datums today are those of the World Geodetic System, or WGS. In fact, Doppler satellite images were used to create a new, more accurate World Geodetic System, which eventually became known as WGS 84. GPS receivers or global positioning systems use often the WGS84 datum for measurement. We'll be talking more about GPS and latitude-longitude coordinates coming up. But first, let's take a look at a simple example as it relates to a very simple coordinate system. In Euclidean geometry, the Cartesian coordinate system specifies that each point, uniquely in a plane, can be specified by measured distances from the origin. Euclidean geometry is a mathematical system focusing on points, lines, and angles on a flat plane. Well, this is a Cartesian coordinate system, a very simple Cartesian coordinate system. Just keep in mind that coordinate systems used in a GIS are much more sophisticated, complicated, and detailed than this example. If we wish to plot the following points, represented as 2, 3, 5, 2, and -2, 3, remember that the first number in each of our points represents the x-coordinate, or how far we move from the origin along the x-axis. Values to the right of the origin are positive, values left of the origin are negative. The second number in each of our points represents the y-coordinate. In other words, how far we move up or down from the origin. For our first point of 2, 3, we move 2 units to the right on the x-axis and 3 units up on the y-axis. For the second point, we move 5 units right of the origin and 2 units up from the origin. For our last point, we move 2 units to the left of the origin along the x-axis and 3 units up on the y-axis from the origin. Keeping it very simple, let's take a look at the state plane coordinate system as it relates to the state of Montana in the U.S. The point at which the x-axis and y-axis intersect is known as the origin. It has a coordinate value of 0, 0. For this example, we're going to consider this as a simple Cartesian coordinate system. If we wanted to refer to a point, such as this point, it would have this set of coordinate values. Now, this simple portrayal of the state plane coordinate system has been very generalized for this example. Under the surface, this spatial reference system uses a map projection of Lambert conformal conic. It uses a horizontal datum titled the North American Datum of 1983. The planar distance units are in meters, and it also uses a state plane zone identifier of 2500. In very simple terms, we can think of a spatial reference system as a simple Cartesian coordinate system. A coordinate system of mathematics and geodetic constants that define how a specific geographic location is converted is inherently much more complicated. The universal transverse Mercator coordinate system is a grid-based method of specifying locations on the surface of the Earth, and it too is a practical application of a two-dimensional Cartesian coordinate system. The UTM system employs a series of 60 zones, each of which is based on a specifically defined secant transverse Mercator projection. The UTM system divides the surface of our Earth into 60 zones. Each of the 60 zones has a width of 6 degrees longitude. Each of the 60 zones is based on a transverse Mercator projection. A position on our planet is referenced in the UTM system by first the UTM zone and then an easting and northing coordinate pair. Easting and northing refer to an x-y coordinate pair. The easting is a projected distance of the position eastward from the central meridian, and the northing, or the y, is a projected distance of the point north of the equator, or south of the equator if we're in the southern hemisphere. The UTM coordinate system and the state plane coordinate system, along with many others, are complex. In other words, there's a lot of mathematical computation that goes into a coordinate system, projection, and datum. Geographic data represented by its spatial location is often referred to as georeferenced data. A projection can be defined as the transformation of the round Earth, which has 3 dimensions, into a 2-dimensional surface. Whenever we take a real 3-dimensional object, such as planet Earth, and project it to a 2-dimensional object, such as a flat piece of paper, Distortion is always introduced into the projected data. Any map that we look at on a piece of paper or in 2 dimensions has inherent distortion. This distortion may come in the form of shape, area, distance, and/or direction. Let's take a look at a very simple example. Imagine we have an orange. This is where OJ comes from, not OJ juice. By removing the orange peel, which originated as a 3-dimensional object, we can make an attempt to flatten that orange peel so it occupies only a 2-dimensional space. The result is we projected a 3-dimensional orange peel onto a 2-dimensional plane. I wonder if we could call this the orange zest projection. A map projection is any method of representing the surface of a 3-dimensional sphere onto a 2-dimensional plane. Projections are a necessity to generate a 2-dimensional map. Why? Well, we're going from a 3D surface to a 2D surface. It's just that simple. A map projection is a mathematical transformation. The word projection originates from the concept of projecting light. Imagine a light source inside of a globe. That light is illuminating the surface of the Earth, such as land masses. If we were to hold a piece of paper around that globe, those surfaces would be projected onto the paper as projected shadows. The term cylindrical projection can be thought of as wrapping a piece of paper around a globe where the resultant shape of the paper is a cylinder. After constructing and wrapping the paper around our globe and then projecting the surface of the Earth or globe onto the cylinder, we can subsequently unfold the cylinder. The result is that our cylindrical projection shows the whole Earth as a finite rectangle. Repetition and repetition. Remember that all map projections distort the surface of the Earth in some way. Either area, shape, direction, bearing, distance, or scale are distorted. No projection is free from all distortion. Cartographers and GIS users must select a projection which will result in the minimum distortion in relation to the map theme or purpose. Map projections are grouped into 3 primary families, including conical, cylindrical, and azimuthal. With a conic or conical projection, points from the globe are transferred to a cone which has been enveloped around the sphere. Conic projections are often used in a project where the area has a greater east-west extent than a north-south extent. Cylindrical projections, think of a cylinder, are formed by wrapping a large flat plane around the globe to form a cylinder. This family of projections is often used to represent the entire world. Cylindrical projections enable measurements of angles and distance. The azimuthal projections project a picture or a portion of the Earth as a flattened disk. All directions are preserved from a reference point. The azimuthal projection is also called a plane projection. Normally only one hemisphere or a portion of the hemisphere is represented on an azimuthal projection. There is a variety of compromised projections that give up the idea of perfectly preserving metric properties. Instead, they seek a balance between distortion and simply to make things look pretty good. An example of this is the Robinson projection, which was produced by Arthur Robinson in the early 1960s at the University of Wisconsin-Madison. This is a projection used by Rand McNally. Arthur Robinson sought to establish cartography as a recognized discipline and ultimately granted both undergraduate and master's degrees in cartography in Wisconsin. Maps are one of the oldest types of documents in existence, and for some time people thought our planet was flat. Most of us believe the planet is not flat, although there is a society called the Flat Earth Society. Check it out. From what I can gather, the Flat Earth Society believes the Earth is flat, though I think it might just be a joke. When we project the 3-dimensional surface of the Earth onto a 2-dimensional mapping plane, we use a reference surface for large-scale map, and this is typically called an ellipsoid. Ellipsoids that model the Earth's surface are very near to being spherical, so close that they can be called a spheroid. Probably the most commonly used coordinate system today is the geographic coordinate system, often referred to as longitude, latitude, and the height system. The important thing to consider is that longitude and latitude represent angles. The prime meridian and the equator are the reference planes used to define these angles. Any point on the Earth's surface can be referenced using a longitude, latitude, and a height value. Degrees of longitude and latitude can be further subdivided into minutes and seconds. There are 60 minutes per degree and 60 seconds per minute. Longitude can be defined as the angular distance of any point on Earth measured east or west of a point on the Earth's surface. The world's nations have agreed that the prime meridian, which passes through the Royal Observatory in Greenwich, England, serves as the reference for longitude and is the designated 0 degrees longitude. Because this designation of longitude is measured in degrees west or east of the prime meridian, the common practice is to use an east or west designation to distinguish if the reference angle is west or east of the prime meridian. Longitude angular measurements stored in a GIS often have a negative value if the angle is west of the prime meridian. When using a GPS receiver, the GPS taps into atomic clocks and satellites to measure this value accurately. The Earth is divided equally into 360 degrees of longitude, with 180 degrees being east of the prime meridian and 180 degrees west of the prime meridian. If we mapped the location of a fire hydrant in Seattle, Washington, which is west of the prime meridian, the resultant longitude-latitude values would look like this. The prime meridian, which is that 0 degree mark in today's longitudinal system, is also called the international dateline. It designates the place or location where each day officially begins. Now, the dateline has nothing to do with the date palm, a palm tree cultivated for its edible fruit. Though if you're hungry and in Greenwich, England, you could probably stand in line and get a date, which may be called the dateline. Latitude is the angular distance of any point on Earth's surface measured north or south of the equator in degrees, minutes, and seconds. We can think of the equator as an imaginary line on the Earth's surface that is equal distant from the North Pole and South Pole, which divides the Earth into a southern hemisphere and a northern hemisphere. The equator is considered 0 degrees latitude. Values of latitude increase north of the equator and are considered positive values. Values south of the equator decrease and are represented with negative values. Some people envision a ladder to help them distinguish longitude and latitude. Think of the rungs in the ladder as lines of latitude. Imagine we travel to the very center of the Earth. I know it sounds far-fetched, but just stick with me on this one. You might get the point across. And we won't take our ladder with us. We're now in the center of the Earth, and I have in my hand 2 laser light pens that emit light from an LED laser. The latitude pen is turned on and is emitting a red light. Holding the pen at the same angle as our imaginary disk formed by the equator, in other words, 0 degrees latitude, the line formed by the laser as I rotate around is sometimes called a parallel. We also know that this line that we created is 0 degrees latitude, also known as the equator. Why is it 0 degrees? In relation to the horizontal plane, the light pen is angled at 0 degrees. Using my body as a vertical plane, I'm going to pivot the light pen 45 degrees north. This angular measure of 45 degrees is from the imaginary plane that we call the equator. Keeping the light pen at this angle, if I were to rotate my body around, the imaginary line formed by the laser light would be 45 degrees north latitude. I will relinquish our latitude pen and sacrifice it to the monsters at the center of the Earth. We could repeat this experiment with the longitude pen using the international dateline or the prime meridian as our starting angle and rotate accordingly. Recall that longitude is typically used for east-west measurements. And like latitude, longitude is given in an angular measurement ranging from 0 degrees at the prime meridian to plus 180 degrees eastward and minus 180 degrees westward. If you travel to Yellowstone National Park in North America, if you're traveling between Gardner, Montana and Mammoth Hot Springs, you may come across this sign that says you're at the 45th parallel of latitude, halfway between the equator and the North Pole. If we look at the 45th parallel of latitude superimposed on a globe, we can see indeed it is halfway between the equator and the North Pole. What other communities or cities lie halfway between the equator and the North Pole? A thermometer can be used for all foods when cooking. It measures the internal temperature of your cooked meat, poultry, breads, and casserole. By reaching a certain internal temperature, certain strains of harmful bacteria, such as E. coli, can be destroyed. This temperature has nothing to do with degrees of latitude or longitude. Using the geographic coordinates of longitude, latitude, we can represent the position or location of any point on the Earth's surface using these angles. Here are a couple things to keep in mind when using geographic coordinates of longitude, latitude. Longitude, latitude coordinates can be expressed in degrees, minutes, seconds, and decimal degrees. I say this rather loosely, but working with data stored in decimal degrees is often easier than data stored in DMS. Many utilities exist which facilitate the conversion of data stored in degrees, minutes, seconds to decimal degrees. Current use of GPS and GIS software has increased the awareness of the importance of recording the datum and the ellipsoid for longitude-latitude. Knowing the datum and the ellipsoid that your longitude-latitude values are stored in can make a big difference in the position of that feature on the Earth's surface. If you receive data that were collected using the WGS84 datum, but you tell the GIS the data are stored in the North American datum of 1927, your GIS will show these positions in the wrong location. Geographic coordinates stored in longitude-latitude angles can be projected to other coordinate systems. Lucky for us, ArcGIS Desktop, specifically our toolbox, provides us with the tools to perform this task. Alright, next we are going to look at a series of tools as part of ArcGIS Desktop that will help us to project or reproject geographic information assets from one spatial referencing system to another spatial referencing system. In addition, we will look at procedures for defining a spatial referencing system and importing a spatial reference from an existing spatial asset. We have been discussing map projections. Though I just used the term spatial referencing system, what's the difference in terms? Let's review an important definition before we start using tools to project or reproject our spatial data. When referring to the spatial reference of a geographic information asset, the term spatial reference or spatial referencing system consists of a projection, but it also includes a coordinate system and a datum. In the realm of ArcGIS Desktop, it can also include different resolutions. Elevation uses a Z resolution. Routes and networks, which use a linear-based measurement system, use an M resolution. Oh yeah, don't forget XY resolutions and XY tolerances. In simple terms, the spatial reference of a geographic information asset is a package deal. It includes the coordinate system, the datum, the projection, and numerous other components or elements, including tolerances and resolutions, which define the home for our spatial asset. Often the term project or reproject is used to describe the process of moving a geographic information asset from one spatial reference to another, though the name project sounds a little bit like projection, and it can be a little confusing, so keep that in mind. Within the realm of ArcGIS Desktop, virtually any geoprocessing task that we perform on a geographic information asset requires that geographic information asset have a defined spatial reference. Even if we wish to perform a simple measurement of distance or calculate the area of a polygon, a spatial referencing system is required. ArcMap, a component of ArcGIS Desktop, can perform what is known as an on-the-fly projection. This has nothing to do with the common housefly, known as Musca domestica. In simple terms, here's a simple overview of on-the-fly projections. Let's assume we start with a fresh copy of ArcMap. The first spatial asset we add to ArcMap ends up in a data frame. By default, that data frame is called layers. And the first spatial asset we add to that data frame defines the spatial reference for that data frame. Now, this is where on-the-fly projections come into play. If we then attempt to add another geographic information asset to that data frame, but that other asset is in a different spatial referencing system, ArcMap will make an attempt to show us that second spatial asset using the coordinate system that was defined initially. This certainly is a pretty cool aspect of ArcMap, though the on-the-fly projection activity can greatly affect drawing performance and can result in issues in displaying data, including raster data. In addition, if our goal is to perform geoprocessing tasks, including overlay analysis, buffer analysis, or other proximity analyses, in most cases the analysis tools require that all features are in a common coordinate system. This is one of the reasons we project data from one coordinate system to another. No matter what we are mapping, be it a fire hydrant or a cheetah running across South Africa chasing an impala, or a cheetah chasing a fire hydrant, a spatial referencing system is necessary for displaying and creating spatial assets for the GIS. And for any given dataset, including the positions of that cheetah chasing the impala, that dataset can be projected to, sometimes referred to as reprojected to, virtually any spatial referencing system. If you are working on a GIS project, more than likely you will need to bring together and associate diverse sources of geographic information assets. And yes, each data source could be stored in a different spatial referencing system. All right, are you ready for a few examples? Well, first we'll define the spatial referencing system of a geographic information asset. Then we will project or reproject a geographic information asset from one spatial referencing system to another. I've opened a fresh copy of our catalog. Our KnowGIS 10 training series consists of over 16 hours of comprehensive material providing foundation training on ArcGIS Desktop version 10. We have established a folder connection to the subdirectory called GCS, which stands for Geographic Coordinate System. All of our project data is included with the KnowGIS training series. After the folder connection has been made, we now have access to the contents. Let's take a peek and see what is in this folder. After expanding the folder connection of GCS, we observe 4 files. After making the Preview tab active and verifying that the preview mode is set to Geography, we can get a preview of each of the 3 spatial assets in this directory. Each of the files with a yellow icon are ESRI shapefiles. Notice the .shp extension. To view the shapefile properties, using the pointer, right-click on the file, for example, management.shp, and choose Property. Within the Shapefile Properties dialog box, make the XY Coordinate System tab active. We observe the name of the geographic coordinate system is NAD, 1983 State Plane, Montana, FIP Zone 2500. In addition, the details of the spatial reference system are provided to us, including the name of the projection, Lambert conformal conic, and other important details. All right, so the geographic information asset called management.shp has a defined spatial referencing system. If we repeat the same procedure with the shapefile called easement_geographic.shp, it is evident that the name of the spatial referencing system is GCS_North America_1983. In other words, this spatial asset is unprojected and stored in a geographic coordinate system. Remember, angular coordinates, longitude, latitude. What is the spatial referencing system for county.shape? Right-click, Properties. Interesting. The spatial referencing system for this spatial asset is unknown. Well, it really isn't unknown because we were provided with a simple text file. We've loaded this file by double-clicking on it within the catalog tree. The text file appears to provide us with the necessary information as to the spatial referencing system. Though ArcGIS Desktop is unaware of the text file, so it is unaware of the spatial referencing system. One of our goals is to fix this issue. All right, here's our plan. Because we were provided with information on the spatial referencing system for county.shape, we will employ a tool called Define Projection to define the spatial referencing system for this spatial asset. I love the search window. Let's use the search window to find the tool called Define Projection. I'll click on this icon here to invoke the search window. We can search for maps, data, and tools. We're looking for a tool. I'll type in Define space Project and then click the magnifying glass. Note the hammer. This indicates a tool. The name of the tool is Define Projection, although really it's Define Spatial Referencing System. If we click on the hyperlink, which appears in green, we will be presented with the tool's location in the catalog tree. All right, let's invoke the tool and use it. We'll do that by double-clicking on it within the catalog tree. We are presented with the Define Projection dialog box. We need to specify the input dataset or feature class that we are going to define the projection for. Then we specify the spatial referencing system, which is referred to as a coordinate system in this dialog box. Note it is currently set to unknown. Alright, as a review, the text file we were provided shows a spatial referencing system of state plane, Montana, FIPS zone 2500, using the datum of North American datum of 1983. One option is to browse for the spatial referencing system. After clicking the Select button, we can begin browsing for a coordinate system. The coordinate system we are looking for is a projected coordinate system, state plane, using the North American datum of 1983, specifically meters, and the name of the coordinate system is NAD 1983 state plane, Montana FIPS zone 2500.prj. We'll select that and choose Add. As part of our quality assurance, we'll compare the contents of the text file with the details of the spatial referencing system shown in the Spatial Reference Properties dialog box. The details appear to match. Let's click Apply and OK. We are made aware that the Define Projection tool is working based on the horizontal text, the blue text that appears here. All right, let's scroll to the top of the catalog tree. Using the pointer, right-click on counties.shape. Perfect. The spatial referencing system has been defined. All right, everything will be okay. So let's click OK. Let's look at the other shapefile called easement_geographic. This spatial asset has a defined coordinate system of GCS_North America 1983. Let's define our goals. We will attempt to reproject the spatial asset called easement_geographic from its existing spatial referencing system to the spatial referencing system that both county and management are stored in. In other words, we will reproject the easement geographic shapefile, essentially creating a new shapefile to match the spatial referencing system of both county and management.shp. This is very easy. Using the search window, search for the tool called Project. Very good, there it is. Next, click on the hyperlink below the tool to locate it in the catalog tree. In the catalog tree, double-click on the tool to invoke it. First, we define the input dataset or feature class, which will be easement_geographic. After clicking Add, note the input coordinate system is revealed to us in gray text. Now we will define the output dataset or feature class. We'll enter a new name of just easement.shp, stored in the GCS directory. Now we have two options for defining the output coordinate system. Sure, we could browse for a coordinate system like we did before, and there's nothing wrong with this, though because two of the other geographic information assets have a defined coordinate system that we want to use, we can import that coordinate system from either of the two geographic information assets. Let's try this. Click Import. So we can import a coordinate system and X, Y, Z, and M domains from an existing geographic information asset. And we'll select county.shp. After clicking Add, we are presented with the XY coordinate system. This looks correct. Then we apply the changes and click OK. Assuming the Project tool was successful, we will probably see a pop-up window with a green checkbox next to the phrase Project. A critical thing to understand is the reprojection or the projection of data is different from an on-the-fly projection. The on-the-fly projection routine is a temporary display-only activity. Projecting data results in a new data set. In order for on-the-fly projections to work properly, our data set's coordinate system must be defined. In an ESRI shapefile, this projection information is often stored in a file with an extension of .prj. Spatial referencing systems are also stored in a geodatabase for feature classes and feature datasets. Even if our data set is in a geographic coordinate system, but it isn't defined as such, GIS software often cannot perform a projection on the fly because it doesn't know what the data is stored in. We'll look at some examples in later lessons, but just think of on-the-fly projections as a handy aspect of ArcMap's projection capabilities. Any geographic information asset without defined coordinate systems will be displayed in whatever coordinate system they are in. This should be obvious, but it would take an infinitely large database to capture the real world. We, as humans, must somehow reduce real-world phenomena to a finite and manageable quantity through a process of generalization, simplification, and abstraction. Let's take a look at an example. Wheat is a grass, and believe it or not, wheat is the leading source of vegetable protein in the human food supply, having a higher protein content than either maize, corn, soybeans, or rice. Wheat grain is a staple food used to make flour, which eventually becomes bread, biscuits, cookies, cakes, or even cereal. I'm standing next to a wheat field near where my office is. These images, taken in the end of July, show that the wheat is still growing. The grass is still growing. In addition to wheat, there's also weeds growing in the field, and the entire field obviously is not made up of just wheat. There exist vacant areas where there's just soil or dirt. Each blade of the wheat grass consists of a series of berries. These berries are still immature, but eventually the wheat berries, which look like kind of like a piece of rice, will be harvested, dried, and pulverized into a flour. This year there is a threat of a grasshopper infestation due to a moist spring. In addition, there are butterflies flying around. There is an incredible amount of detail going on here, and the field is dynamic. It's growing every day, at least during the growing season. If we were to look at a map generated by local farmers, this map is a generalization of what exists on the ground. The map could be as simple as showing a series of polygons, each polygon representing a field where wheat is being grown. From these polygons, we can calculate acreage or hectares. We could also categorize each field. Each category would indicate the type of wheat being grown, such as common wheat or bread wheat, durum, spelt, emmer, hard red spring wheat, or soft red winter wheat. As humans, these farmers have simplified this incredible array of grass, grasshoppers, weeds, and butterflies into a cartographic representation echoing area, inventory, and crop type. A significant amount of generalization occurred to create this one simple map. This map represents a simple inventory at a current state in time, reflecting a crop on the ground grown by a farmer. We can represent many of the complex features and systems on our planet using layers. Layers like that of an onion. GIS technology is founded upon the capability to organize this information into a series of layers that can be integrated together into a composite view. What is a model? A model is a representation of something, or something on a smaller scale. It can also be a hypothetical description of a complex entity or a process. It's important to emphasize that a model is not the real world, but merely a human construct to help us better understand real-world systems. This real world can only be depicted in a GIS through the use of models. Models define the real-world phenomena in a manner that ArcGIS desktop or computer systems can interpret, as well as facilitate meaningful analysis. Raster and vector are the two basic data models for storing real-world geographic information features on a computer. The human eye brain are highly efficient at recognizing shapes and forms, but computers need to be instructed exactly how spatial information and patterns should be handled and displayed. Although other data models exist, including the object-oriented data model, raster and vector appear to have a pretty strong following. These two alternate methods are used to represent and store most of the spatial information we use in a GIS. The raster data model consists of a matrix of cells, also known as pixels, organized into rows and columns, or a grid, where each cell contains a value representing information. The term tessellation refers to the pattern resulting in or from the arrangement of cells to cover a 2D plane without any gaps or overlaps. Given the raster data model, the basic data unit is the spatial cell. Rows and columns make up a grid. The raster data model is ideal for storing information that is continuous in the real world. For example, elevation, slope, and aspect. Image data from satellites or from airplanes, scanned aerial photographs, and maps are represented using the raster data model. Let's look at an example of the raster data model. I know this may seem kind of crazy, but hopefully it too will get the point across. Imagine you have a window in your house, apartment, flat, or office space. If you are in prison or in jail, imagine you have a window, if you can. And that window has a screen. We're going to remove the screen from the window. Hey, I won't tell anyone. I'm going to take my screen and drop it here on top of all this stuff. Using a marker, I am going to code the surface of the screen based on what lies beneath the screen. Now, as we can see, the screen has a fairly fine resolution, and I'm able to represent or code the features that lie beneath the screen pretty well. The size of the cell on our screen defines the resolution of our data. If we had access to another screen that had much larger cells, our image resolution would be less than that of the screen with a finer cell mesh. Let's look at a potential problem with the raster data model. Given a raster cell size, as shown here, if we inspect this single cell, which has a finite size, and compare it to the underlying object, in this case the handle of a wrench, we see that the handle of the wrench occupies only half or maybe less than half of that finite cell. This cell can be coded with only one value. What do we code it with? Wrench handle or concrete? See, that's the problem. One option is to decrease the cell size, resulting in a higher resolution raster dataset. With a greater number of cells, we can more accurately represent the real-world features. There's a trade-off. With a higher resolution image, the resultant file size is larger and takes more space on our hard drive. For example, Landsat offers imagery at a 30-meter ground resolution. Kestrel Aerial Services offers imagery at a 6-inch ground resolution. What are other examples of raster data? A satellite image, digital elevation models or DEMs, digital orthophotos, digital raster graphics or DRGs, and a scanned aerial photograph. To represent a point feature with the raster data model, we'd have something like this. To represent a linear feature such as a road or stream, it may look like this. Areas in raster would look something like this. The raster data model uses raster data structures to store data. Examples of raster data structures include exhaustive enumeration, run length encoding, and the quad tree. Raster data can be compressed to reduce the data volume. There's a variety of techniques available for image compression. Compression techniques can be considered lossless or lossy. Lossy compression is a data compression method which discards or loses some of the data in order to achieve the goal of a smaller file size. I think the name lossy would be a great name for a dog. Or wait, was that Lassie? As an example, the TIFF image format is lossless, meaning it retains all of the information, whereas a JPEG image is considered a lossy compression where data are lost or given up, in other words, but the result is a smaller file size. The advantages of the raster data model include the idea that data can be represented at nearly its original resolution and form without generalization. In addition, the raster data model facilitates fairly straightforward overlay operation, also known as map algebra. And often the graphic output of raster data is more aesthetically pleasing as compared to vector data. Alright, so what are the disadvantages of the raster data model? Well, raster data often requires more storage space than representing data in the vector format. Raster can be more difficult to register, scale, and reproject, again, as compared to vector data. And not all real-world phenomena relate directly with a raster representation. In this example, if we zoom in pretty tight to a linear feature such as a road, we notice kind of a checkerboard appearance. This is also known as aliasing. Here's an interesting question for you. You just purchased a fancy digital camera. This camera has a CCD or charge couple device that results in a 18 megapixel image. We are in a small single engine airplane and we are now taking off from the runway. If you were to point the camera out of the airplane window and take a shot, could you use the resultant image in GIS? The image you captured would be considered an oblique view image. It has inherent distortion, not only from the lens of the camera, but also from the position and movement of the plane we are traveling in. Before an image can be useful within a GIS, the image or aerial photographs must be prepared in a way that removes distortion from the image. This process is called orthorectification. Orthorectification removes distortion and corrects the image so that scale is uniform. It also adjusts for topographic relief, camera tilt, and the spherical lens distortion. All images used as a backdrop in GIS for digitizing or other activities should be orthorectified images. The vector data model uses discrete XY coordinates to represent spatial features. These coordinates are used to represent points, lines, and polylines, and polygons. An example of a point may be a fire hydrant or a water well. An example of a line or polyline may be a road, stream, or a pipeline. An example of a polygon may be a vegetative land type or land ownership. Earlier we talked about coordinate system. In this simple example of a Cartesian coordinate system, each point is uniquely identified on a plane by a pair of numerical coordinates. Those coordinates are determined by the x and y axes. The vector data model is used to store spatial data. Primitives of the vector data model are the point, line, and polygon, and virtually all objects can be built from these simple primitives. Discrete features such as a fire hydrant, a stream, and data summarized by area are often represented and stored in the GIS using the vector data model. Discrete data, or data that the vector data model is good at representing, can be defined as discontinuous data. Unlike the International Harvester pickup truck model S120, which was discontinued, discontinuous data can be defined as data having discrete, known, definable boundaries with an edge. For example, a lake. A lake has a high water mark or an edge defining its boundary. A road, in simple terms, has a definitive edge. Land ownership or cadastral survey has a definitive edge. In other words, discrete data doesn't necessarily have a continuous surface like elevation data. A point is a zero-dimensional object and has only the property of location, x and y. I know it's kind of hard to get our heads around this idea of a zero-dimensional object, but in the GIS, a point represented with a coordinate pair has 0 dimensions. A point with 0 dimensions can be symbolized on a map using a map symbol. And sure, the map symbol appears to have 2 dimensions. A line, no, not a lion. A line is a one-dimensional feature that has a direct link between 2 endpoints. These endpoints are often referred to as nodes or vertices. For some reason, I just had an image of a lion's nose in my mind, almost like line node. Yeah, I know I'm crazy. A line has a length but no width, one-dimensional. Multiple lines can be melded together to form polylines. A polyline that has shape, in this example, starts with a node, and the shape variant is produced by adding a vertex. A vertex is kind of like a hinge and allows the line to change direction and shape. A polygon is a 2-dimensional object with properties of area and perimeter. In geometry, a polygon is traditionally thought of as a bounded closed circuit made up of a finite sequence of straight line segments. Circles, squares, rectangles, triangles are all considered polygons. Poly means many, so many sides. More than likely, a polygon used to represent the perimeter of a lake would be irregular in shape. The vector data model uses vector data structures to store and represent the data. Examples of vector data structures include the spaghetti or simple data structure, the topological data structure, which stores relationships between features, and the object-oriented data structure. Each entity stored in the vector data model can have one or more data attributes. An attribute is a characteristic or quality of a thing. Attributes describe map information and are the specific qualities, quantities, and characteristics of an entity. If we look at the attribute table of a lake stored as a polygon, we can see the following information. The attribute information is stored in a database. Let's look at a simple example as it relates to an ESRI shapefile. The ESRI shapefile is a digital vector storage format for storing geographic information assets. It stores both the location and the associated attribute information. Shapefiles are considered to be pretty simple because they store primitive geometrical data types of points, lines, and polygons. This format lacks the capacity to store topology. We'll briefly discuss topology in a little bit. An ESRI shapefile is comprised of three primary components. The three primary components of a shapefile include a file that stores the spatial geometry, also known as the feature geometry. This file has an extension of .shp. A second file that stores the attributes in a table. This attribute table has an extension of a .dbf, which is a takeoff from DBase files. The third file stores a link between the spatial geometry and the attribute table. This file stores a positional index, also known as a shape index format file. This file has an extension of .shx. In earlier days, basically the first generation of GIS, attributes and spatial information were stored separately. The shapefile is a good example of this. Specialized file structures were then used to handle the spatial data. The geodatabase is a relatively new but also common data storage management framework for ArcGIS and other spatially enabled software systems. Instead of having multiple files, the geodatabase promotes the concept of a data repository for spatial data, where geo is the spatial data and database is the database component. The geodatabase also offers sophisticated rules and relationships for our data, and with the geodatabase we can store a very rich collection of spatial data in one location. An advantage of the geodatabase is it supports topology. Well, what is topology? Topology is from the Greek word topos, which means place, and logos, which means study. Topology is a major area of mathematics and is also part of spatial properties of objects. Topology is a set of rules and behaviors that model how points, lines, and polygons share geometry. Topology helps us manage GIS data and maintain data integrity. We can define relationships between features with topology. An example would be two adjacent features, such as these land parcels. These land parcels are part of what is known as a cadastral survey. These lots have a common boundary between them, and therefore they share an edge. Features can share geometry within a topology. One of the advantages of topology is it helps us construct new features, such as polygons from lines or lines from polygons, and it helps support relationships and queries of our data. Here's an example of topological elements and their associated relationships. This linear feature has stored in a database information on the polygon to the left of it and to the right of it. A line is made up of vertices and nodes along with direction. The face can be a polygon or a defined area. There is a tremendous range in the types of data used in a GIS. Obtaining and gathering source materials or geographic information assets can be difficult and daunting. It can also be a lot of fun. Some organizations claim that up to 80% of their cost relates to creating new data for the GIS. The type and quality of geographic information assets will vary greatly from project to project. And as a GIS practitioner, we should be aware of the most commonly available data sources. Government agencies often publish a variety of geospatial data, often referred to as portals or repositories, facilitate the dissemination of spatial data. In addition to government agencies, we can also purchase data from commercial entities or even create our own data. Spatial data are available from a variety of places. It is up to us to pick and choose what works best for our project. To help us determine whether or not a spatial data set is right for us, we can read and view associated metadata. Metadata is loosely defined as data about data. Assuming the geographic information assets that we obtain include metadata, we can learn all about the data by reading the metadata. Description and keywords meta tags are commonly used to describe the source of the information, the quality, spatial reference, and overall limitations of the data. Let's explore data sources. Global satellite navigation systems, which consist of a series of constellation satellites, are effective systems for collecting data, spatial data, which eventually can be ported into a GIS. Global Positioning Systems, or GPS, are space-based global navigation satellite systems that were created by the U.S. Department of Defense. GPS provides reliable location and position information in virtually all types of weather. The system works well when the GPS receiver has an unobstructed view of the satellites. Using a GPS receiver in a cave or deep underground may prove to be not too good. A GPS receiver calculates its position by timing the signals sent by the GPS satellites. The satellite vehicles are almost 11,000 nautical miles from our planet. 4 satellites are ideal for normal operation, although more are better. 3 or less often do not provide enough information to solve a position. Different grades of GPS receivers exist, including recreational grade, mapping grade, and survey grade. More advanced GPS receivers include an input for differential correction. The use of differential correction often results in data that has a higher degree of accuracy as compared to, for example, a simple recreational grade GPS. Positions recorded with a GPS receiver can be output to a GIS. Positions are often stored in geographic coordinates or longitude-latitude. By the way, what is the difference between accuracy and precision? Accuracy refers to the closeness between measurements or observations and their expectations or true values. The farther a measurement is from its expected value, the less accurate it is. Precision relates to the closeness to one another of a set of repeated observations of a random variable. To measure precision, a number of measurements are needed. If observations are clustered closely together, we can consider these observations to have been obtained with high precision. Precision does not require us to know the correct or true value. In this simple graphic, the center of the circle represents the true location. This cluster of points shows the positions as being not very accurate and not being very precise. This graphic shows a high degree of precision, but a low degree of accuracy. And finally, this reveals a high degree of accuracy and high precision. 2 other words that are commonly confused, at least in the English language, are farther and further. According to the Merriam-Webster's 10th Collegiate Dictionary, farther is used to describe physical distances. Further is a metaphorical figurative distance. Some argue that farther and further have been used interchangeably throughout history. Examples include, how much farther is it to the fuel station? Or, you couldn't be further from the truth. The Compass navigation system, also known as BD2, is a project by China to develop an independent global satellite navigation system. The new system will be a constellation of 35 satellites, with the majority of the satellites in a medium Earth orbit and a few in a geostationary orbit. The BD2 system will offer complete coverage of the globe. In this example, data were collected using a GPS receiver. This linear feature represents a trace obtained by walking along a trail. Using translation software, data collected with the GPS is translated to a format that a GIS can digest. In this example, the resultant data has been stored in an ESRI shapefile. The translation software automatically created the spatial reference information, and when we add this geographic information asset to ArcMap, for example, ArcMap can perform an on-the-fly projection to align this GPS data with other reference data. If we take a closer look at the data collected by walking with a GPS receiver, we observe that this line, made up of many vertices, is not very clean. Each vertex represents a second in time of GPS data collection. In summary, just remember that it may take additional time and effort to clean up these extra vertices. This is considered data editing. In this example, cleaning up the data involves removing extra vertices in our line data. Assuming the GPS receiver collected a location every second, just our walking and swaying may have resulted in these extra vertices. If we wish to create our own data, we can perform heads-up digitizing, construct either point, line, polyline, or polygon features, and then assign attributes to those features. Often during the heads-up digitizing activity, a background map, aerial image, or satellite image is used to help us identify features. Geocoding is the process of finding associated geographic locations or coordinates from other geographic data, such as street addresses or zip codes. If we have a list of customers, including their address and zip code, through a process of geocoding or address interpolation, we can identify the approximate locations of those addresses. Geocoding takes an address and matches it to a street and a specific segment, such as a block in a town. Online data sources allow us to download data or view data from Internet map servers. One of the easiest ways to find data online is to perform a web search. Look for GIS data portals, search government agency websites, and also look at GIS web servers. In the United States, the Geospatial Data Gateway is a one-stop source for environmental and natural resource data. Environmental Systems Research Institute, or ESRI, is not the only company producing software or applications that facilitate GIS activities. Other commercial GIS applications that are available include Manifold, Global Mapper, MapInfo, and Everest GIS. Specialized mapping software includes Surfer, which is a contouring and 3D surface mapping program, and SURPAC is a comprehensive system for ore body evaluation and open pit and underground mine design. There are many others available as well. This is just a short list. According to the software manufacturer, an advantage of the Manifold system is that it offers an extremely powerful, full-featured, and modern geographic information system at a low price. Manifold also includes a world-class Internet map server, an object library and development environment to create custom applications. Global Mapper is considered an easy-to-use viewer and editor capable of displaying the most popular raster, elevation, and vector datasets. Global Mapper facilitates conversion, editing, mosaicing, reprojecting, printing, and tracking GPS data. GIS can be used for a number of activities, including just the simple inventory of existing features. A landowner in New Mexico may wish to create an inventory so that he or she can visualize existing features on a property. This inventory may include just areas that are currently being used to grow crops, building locations, existing water springs that can be used to quench the thirst of horses and cows. This activity of inventory is a powerful use for GIS, but there's a lot more we can do with GIS. Spatial analysis adds value to geographic data and turns raw data into useful information. The history of spatial analysis starts with early cartography. Cholera morbus is what we now call just cholera. Apparently the disease was first noticed among British troops in India In the early 1800s, people believed that cholera, or the Black Death, was caused by pollution or bad air. And in the 1800s, people were amazed at how quickly cholera spread through a community. Cholera is considered a bacterial infection which affects the small intestine. Severe dehydration caused by diarrhea and vomiting can lead to death. Following the outbreak of cholera in the Broad Street area in London in 1854, John Snow, a physician, started talking to local residents and identified the source of the outbreak as a public water pump on Broad Street. John Snow generated two maps, and on one map he placed an X to represent the locations of water supplies. Small dots were used to represent the locations of homes of people that died. Apparently at this time, chemical and microscopic examination was not very powerful, though John Snow did attempt to convince and persuade the local council to disable this well pump and remove its handle. Apparently this action has been popularly reported as ending the outbreak. This simple map showing clusters of cholera cases is an example of spatial analysis. It helped John Snow and others see patterns and factors affecting the health and illness of people. By the end of this outbreak, over 600 people died. No one really knows, so I'm only guessing here, but more than likely, some of our cartographically inclined ancestors may have used mapping and spatial analysis as well, way before the 1800s. Let's briefly discuss a few definitions as they relate to spatial analysis. Modeling, or a model, is an abstraction of reality. Synthesis is to combine or meld separate parts or elements to form a more complex element. Analyze is to separate into parts in order to identify or to study a structure. Let's explore different types of spatial analysis. Queries and reasoning are pretty much the most basic of analysis operations. Through queries, we can ask questions, and the GIS provides answers. During the query operation, typically new data is not generated. Examples of a query based on selection by attributes may include find all wells that have a depth greater than 100 feet. Find all wells that have water with a pH level equal to 6.5. These examples are non-spatial selections by attribute. A spatial search or spatial selection incorporates the geometry of features. In this example, we can select all water wells that are within 1 mile of a known pollution source. What is the significance of a 1 mile search radius? I certainly can't answer that. I do know 1 mile is 5,280 feet, but how about 5,234 feet? Measurements are also considered a type of spatial analysis. Measurements help us describe spatial data to include their properties of length, area, shape, aspect, or slope. Measurement also describes relationships between objects, such as distance and direction. After identifying forested areas that were either damaged or killed due to beetle infestation, I'm not talking Ringo Starr or Hey Jude either. The mountain pine beetle is a species of a dark beetle native to forests in western North America. Pine beetles have a tendency to kill trees by boring a hole into the bark where they feed and also lay eggs. After an outbreak, a grove of pine trees may appear to have a red canopy as shown here. After digitizing these areas and creating polygons, we can instruct the GIS to calculate the area of each polygon. This simple inventory, reflecting polygons of affected areas, have the potential to help foresters and scientists understand the spatial distribution of the situation and the approximate area that has been affected. Digital elevation models, which are digital files consisting of terrain elevations for ground positions, also known as a raster dataset, can be used to generate three-dimensional graphics displaying terrain, slope, aspect, and profiles of selected areas. We can produce a new aspect data layer by feeding the digital elevation model through specialized GIS software. A GIS practitioner can use the aspect calculations for additional analysis. Transformations are also considered a type of spatial analysis. The basic approach to a transformation is to take data and transform it into new data. Examples of transformations include dissolving data, buffering, union, intersect, point-in polygon analysis, and a spatial join. In the dissolve operation, aggregate items that have the same value can be grouped together. Typically, the dissolve results in a less detailed data set as compared to the original data set that was used as input. The buffer operation generates a zone or a new area around an existing map feature. Points, lines, and polygons can be buffered. The result of the buffer operation is a data set that can be used for proximity analysis. In this example, an individual well could be buffered 1 mile. The result is a polygon with a radius of 1 mile. Spatial overlay allows us to join and view together separate data sets that share all or some of the same geographic area. Overlay operations involve the placement of one geographic information asset on top of other geographic information assets. In this spatial overlay example, we're performing a point-in polygon overlay. Two separate geographic information assets, one representing wells and the other one representing land ownership as polygons, are overlaid on one another. As a result, the point attribute table representing wells is populated with ownership information. Other examples of spatial overlays include union and intersect. The union of two geographic information assets, such as A and B, result in a new geographic information asset that contains all elements of A and B, but no other elements. Intersect analysis computes the geometric intersection of the input data sets. A new geographic information asset or data set is generated, which reveals those areas that are common to both input data sets. Descriptive summaries, another type of spatial analysis, help us capture the essence of a data set in one or two numbers, such as the sum or the mean. These numerical or statistic summaries can be used to describe a data set. In the example of our water well data, we can derive descriptive summaries of the depth or the pH. Spatial analysis helps us, as GIS practitioners, derive and create new information from existing data. Newly derived and calculated information as a result of spatial analysis can help us understand the spatial distribution of phenomena that occur around us. Spatial analysis is the activity of applying analytical techniques to spatially referenced data to extract or generate new geographic information. Please keep in mind that the complex nature of spatial problems and spatial features are often well beyond the capacity of current GIS software. We're using human-made constructs or models to represent real-world features that are just super incredibly complex. Humility forces us an opportunity to say, I don't know, or I don't know if GIS has the ability to truly tell me what the answer is. Humility provides a pathway to be open to learning and make space for reflection on how complex our world really is. My philosophy is don't believe everything you see or hear, question everything. Most importantly, be open to new ideas and thought. A few years ago, we were using a numerical model to calculate the spatial distribution of a pollutant coming from a coal-fired power plant. Coal-fired power plants are used to generate electricity and use coal as the source of fuel and energy. Coal-fired power plants apparently are the largest human-caused source of sulfur dioxide, which is a pollutant gas that contributes to the production of acid rain and causes some health effects. Keep in mind that there are natural processes such as biological decomposition, forest fires, and eruptions from volcanoes, which also produce sulfur dioxide emissions. So anyways, we used a numerical model to calculate the spatial distribution of sulfur dioxide emitted from a coal-fired power plant. This numerical model was developed by scientists at the United States Environmental Protection Agency. It took into account meteorological parameters such as wind speed, wind direction, upper atmosphere mixing height, and a variety of other factors as well. The model created a grid, and each cell in the grid was populated with a predicted concentration of sulfur dioxide. The grid was then converted to a raster data set, which revealed color patterns based on the concentration predicted by the model. Because the grid was spatially referenced, the output raster dataset could be overlaid on other geographic information assets, such as rivers and roads. When this map was presented at a public hearing, I noticed some local residents walking up to the map, pointing their finger to the location where they live or where their house is located, and then, through visual spatial analysis, determine whether or not their home was threatened by sulfur dioxide. One person, for example, said,
"Oh, look, our house is outside the pollution. Yeah."
Personally, I was amazed at the limited thought. No questioning of the map, no questioning of where the data came from, no questioning even of the integrity of the model. Possibly a complete disconnect with the realization that pollution and airflow is dynamic and changing all the time. What I'm getting at is that often computational solutions to spatial problems are not possible because of the true complexity of these issues. Unknown variables and conflicts in facts can often result in true questions. In my opinion, it's okay to question everything and realize that maybe we don't have the ability to solve complex spatial problems. The result of any spatial analysis is limited because we as humans are limited. Just keep that in mind when you create a map or visualize a map from someone else. In summary, geographic information systems or geographical information systems are any systems that capture, store, manage, analyze, and present data linked to location. GIS can be a powerful tool in our arsenal of tools. GIS has the potential to help us continue to gain understanding and gain knowledge of the complex systems and features that exist on our planet and other planets. Not only can GIS be used to help us visualize and store an inventory of spatial features, GIS can help reveal patterns, relationships, and trends in the form of maps, reports, and charts. GIS can help us answer questions about these spatial features that surround us. What is where? When is it there? Why is it there? And why do we care? We can visualize where things are, find out what is nearby, view temporal variations in our data, such as what occurs over time, and explore quantities, such as the density of population. A GIS has an appetite for data. Like humans, we can eat a lot of junk food, high fructose corn syrup, monosodium glutamate, refined, processed, and bleached flour and sugar. The end result? Well, I hope all of us are aware of the result. It's important we feed our GIS with good data and not junk data. Please keep in mind that a GIS stores data as a representation of the real world. These data sets are also just a snapshot in time and provide just a static glimpse of the spatial feature. If you are new to the subject of geographic information systems, I would highly recommend that you take the time to check with a local university, college, or adult education center. Determine if they have courses available for you on geographic information systems subjects. If you decide to pursue a degree in geographic information systems, many options are available. You can get a bachelor's degree in geography with an emphasis in geographic information systems, a master's degree in geographic information systems, or how about integrating geographic information system technology with other disciplines such as business, mining, environmental management, or utilities. If you are learning ArcGIS Desktop, the GIS software by ESRI, or if you need a solid foundational refresher course, check out our complete training series called KnowGIS 10. Our training course includes about 16 hours of material, which equates to about a 2-day training course. In just one of the tutorials, we locate a pirate's hidden treasure using the inherent tools of ArcGIS Desktop. Thank you for joining me on this introductory discussion of geographic information systems.